Hello and welcome to today's lesson on energy and um, energy within a chemical reaction. To start with, we need a definition. So energy is the ability to do work or transfer heat. And if we use energy to move something, we call that work. So if we move an object using energy, we call that work. If we change the temperature in an object, we call that heat. We'll talk more about those shortly. This chapter is going to talk about thermodynamics and therefore thermochemistry, which applies to your chemical reactions specifically. For starters, there's a couple different types of energy. The first one's kinetic. The kinetic energy of an object is energy due to motion. And there's an equation for this, which is E sub k, or I always just say Ke. Ke is equal to 1/2 times m times v squared. A couple really important things here. Your energy is going to be measured in joules, and we're going to look at this in a second. Your mass has to be in kilograms, and v has to be in meters per second. So you're going to end up with joules equal to kilograms times, because it's squared up here, it's meters squared per second squared, is the same as a joule. But that is your equation. That's how that looks. And that is kinetic energy, which is the energy of motion. There's also this thing called potential energy. And so potential energy is the energy an object possesses due to its position or chemical composition. Potential energy is based on position or chemical composition, so it has the potential to cause change or do something. That is potential energy. One of the most important forms is we have electrostatic or electrical potential energy. So this is the energy between, like, say, a proton and an electron, or any two charged substances. Equation down here. Energy of electrostatic energy, that's what this EL means here, is equal to K, which is a constant, which we're not going to worry about at this point in time, times Q1 times Q2. Q represents a charge. So Q equals charge. We're going to get more into Q later, but for now, charge is good enough. And then divided by the distance. So you multiply your constant times your two charges and divide that by your distance to get your potential energy. Again, we talked a little bit above units for energy. We use the joule. This is the SI unit. The standard unit for energy is called the joule, which is equal to 1 kilogram times a meter squared, and divide that by a second squared, or kilogram meters squared per second squared is all the same as a joule. We also have this non-SI unit that we use. It's called a calorie. And to go from joules to calories, there are 4.184 joules in 1 calorie. And be careful here, this calorie is not the same as the food calories that we eat and consume and people worry about. A food calorie is 1,000 of these. So 1,000 calories equals what we have. It's called either a kilocalorie, or we use a capital C calorie. And those are all the same. So 1,000 little c calories, or regular calories, is equal to a kilocalorie, which is a big C calorie. That's our food calorie right there. In terms of energy, there's two parts to an experiment that we need to be familiar with. One is the system, and this is what we look at with chemical reactions. So this includes the molecules we're looking to study. So in the picture to the left, we're looking at hydrogen and oxygen coming together to form water. So my system is going to be the hydrogen and oxygen molecules. So for this one, my system is hydrogen and oxygen molecules. The surroundings is everything outside of that. So whether it's placed in water, whether it's in the atmosphere, the surroundings, everything outside of those molecules are considered the surroundings. So that's everything else. And so those two terms you have to know, because we talk about energy moving from systems to surroundings and from surroundings to systems. You have to be able to distinguish between those two terms. Some more vocab that you're going to need. We have a term called work, and we talk about work a lot, but this is a different work than most people are used to. You don't have to go to, we're not going to this kind of work. This work is any energy that's used to move an object over a distance is considered work. So energy used to move an object over some distance is called work. The equation for this, to calculate this, is pretty straightforward, but work equals your force, which is your energy being exerted, times the distance. W is work, F is force, and D is the distance the object, or distance over which the force is exerted. So there is your definition for work and the equation that goes along with it. So if things aren't moving, energy can still be being added and taken away, and this can happen in terms of heat. If we're talking about heat, heat is based on temperature, and so heat always flows from warmer objects to cooler objects. We'll talk more about that here in the next couple of videos. But heat always flows from warm objects to cold objects, and that is really important. It does not go from cold to warm. So heat always goes from hot things to cold things. Or heat goes from hot stuff to cold stuff. And then when this happens, we have energy being transferred. And so there is, energy has the ability to be converted. So this is really important, and this makes up our conservation of energy. Makes up our conservation of energy, which means that energy can't be created or destroyed. But we can convert it from one type to another. So for example, this cyclist here has potential energy because she's not at the bottom of the hill. She's above the ground, above sea level, above whatever lower surface she's on, so she's got potential energy. When she goes down the hill, her potential energy is going to be converted into kinetic energy until she gets to the bottom. Once she's at the bottom, all of her energy is going to be kinetic. She's going to be out of potential. She's not going to have any more that she can gain just by going down a hill. And this constitutes or makes up the first law of thermodynamics. So this is the first law, which states that energy can't be created or destroyed. We should add to the end of this, only transferred from one form to another. So energy can't be created or destroyed, only transferred from one form to another. Ooh. So in other words, the total energy of the system, energy of the universe is constant. So it can go from one form to another. It can go from systems to surroundings, but it has to be picked up somewhere. So if the system loses energy, then your surroundings must gain that energy, and vice versa. So it always goes, one goes up, the other goes down. In regards to energy, yet we still have ones called the internal energy. So this is the energy inside of a system. So internal energy is the sum, the total of all the kinetic and potential energies of all the components of a system. So this includes your chemical potential, your electrical potential, all of that. And this is all internal energy, energy inside a system. We call it E. If we have a change in E, we can calculate that change by taking your final energy minus your initial energy. And that gives us our change in E. So this triangle means delta, which means change in. So final minus initial will give us the change in how much energy we either gained or lost. And some terms that go along with this. If your change in energy is greater than 0, meaning your final energy is bigger than your initial energy, your system absorbed energy from the surroundings. You absorbed energy from the surroundings. We call this endergonic. So we're looking at energy here. We absorbed energy from the surroundings. This is called endergonic. On the flip side, if delta E is less than 0, if we're less than 0, that means your final is below your initial. You had to start with a certain amount and you lost some, which means that you released energy to the surroundings. Your system released energy to the surroundings. This is called exergonic. So endergonic gains energy, exergonic loses energy. And then when we do this, we have an energy exchange between systems and surroundings. This can happen in one of two ways. We talked about different types of energy transfer up above, but your system and surroundings can exchange energy as either heat or work. So your change in internal energy is equal to Q plus W. Your heat change plus your work change. The amount of heat plus the amount of work is all there. And because of this, we can have some signs that go with them. This tells us what's going on. So for Q, again, Q is heat. Whoops. Q is heat in this situation. So Q is heat. And in this case, if it's positive, if Q is positive, that means we are gaining heat. So if Q is positive, we're gaining heat. If Q is negative, because Q is heat and it's negative heat, it means we're losing heat. W stands for work. If it's positive, it means work is being done on the system. Something is working on something else. So it's gaining energy through that work. If it's negative, work is being done by the system. If you do work, you lose energy. And that's what that's showing you. And for delta E, if both are positive, if delta E is positive, that means you're gaining energy. If delta E is negative, that means you are losing energy. So there is more work being done than heat being gained, or there is more heat being lost than work being done. Either way, it kind of works that way. So this is a term you're more familiar with, but if heat is absorbed, so again, we're gaining heat here. If heat is absorbed, we have an endothermic process. Okay, so heat is absorbed, we have endothermic. So on the flip side, if heat is released, we have exothermic. So again, endergonic was energy. So if we gain energy, we're endergonic. If we gain heat, we are endothermic. If we lose energy, we're exergonic. If we release heat, we are exothermic. That's the distinction between those two words. And that's where we're going to stop with this video. So tune in next time. We'll talk about state functions and we'll continue this discussion on heat, work, and energy.